Okay, take it away.
Perfect. Thank you for the still loading. There it goes. Great. Thank you for the introduction. I think one thing that's kind of not listed there is just also have kind of a passion for, trying to make statistics kind of more accessible to kind of everyone. Talking about just at the start, kind of, there is kind of this aura of kind of, mystery and maybe fear about statistics. And while some of the models, can get complex, a lot of the basics and just being understand what's going on are, I think, relatively accessible. And that's really the kind of the goal today is a very big picture kind of overview of statistics, why we need them for research and how we can utilize them without getting too much into maybe the specific techniques used in various scenarios. So the first thing I want to do is just start with some motivation. So this isn't directly a project I've worked on, but it's very related to a few projects I've either have worked on or I'm currently working on. But basically, we want to test if some new app that we can, develop can increase the amount of physical activity. So, whether that's getting little nudges saying, hey, like you haven't walked today, get outside and walk, or whether, it's some other way to, increase motivation or track your physical activity or something like that. We want to see if this new app can increase the amount of physical activity following a traumatic brain injury. Now, we know that creating an app probably is not going to help everyone. So we're not looking for benefit for absolutely everyone, but we are looking at, will this app provide sort of an average benefit? Is giving kind of more help than harm or more help than not? And the way we often assess this is conducting a randomized clinical trial. So we set up a study, we kind of sample individuals, we see how they do, those individuals in that trial do, and then we use that to try to make some kind of conclusion about whether this app is really effective or not. And that's really where this component of statistics really comes in, is we're now trying to make conclusions about this one study, or from this one study, and apply it to as if we had introduced this new app to everyone. So even though it's only tested in a small group, we want to be able to sort of assess as if we had given it to kind of a much larger audience, or ideally the entire population. So this is just an illustration that's trying to kind of capture that idea, right? So we have some population of individuals, and we come up with some new treatment that ideally we want to give to this population, and we hope that it kind of leads to kind of better health. But for a variety of reasons, we're not able to give a treatment to absolutely every single kind of person in the world before we actually, test its kind of rigor. There could be ethical concerns, financial concerns, all kinds of reasons why we can't just say, oh, I developed this new treatment, let's go give it to everybody. So instead, what we do is we really draw this sample from this population, right? So we have kind of these denoted by kind of this green arrow and the green shaded figures, but we draw this sample from the population, and we're able to give kind of a treatment to that sample. And we're then able to assess how does that treatment kind of work, what types of responses are we seeing in that subgroup, that sample that we grab, and then we use our statistics to try to translate that back to the population. So we kind of start with this population, we grab a sample, and then we conduct a study on the sample with our new treatment, and then again, statistics is that bridge that links us back to, okay, we see how it worked in this subgroup, how do we think it's going to work in this population? And to do that, kind of something that says, statistics in 4 measures, these are really, I say, kind of the 4 core measures. And a lot of methods will give you these kind of 4 values. Some of them have, very specific names in specific scenarios. So you're not going to necessarily see these words always pop up. But hopefully, as we kind of walk through what each of these is, hopefully it becomes a little more apparent kind of the role they have in a study. And even if you're not seeing the specific word, point estimate, hopefully it helps you kind of identify what that estimate actually is from that specific study. So again, just kind of going on that list. The first one I want to talk about is point estimate. And this can be viewed as just a single, best guess based off our sample. So again, I think of this as maybe heights. I want to know what's the average height of everybody in the United States. So, I'm going to go out in the street and I'm going to grab 50 random people and I'm going to take the average of all their heights. And that's going to be my single best guess for what the actual height is for the US population. I know it's probably not going to be, perfectly accurate, but I'm hoping if I grab 50 people, I'll at least be, somewhat kind of close. So often this will just be, again, as simple as the average or proportion. So again, in my case, I sampled 50 individuals and I just took their average height. That's gonna be the point estimate. Or maybe if you're counting up, did something happen, did something not? Maybe it's just a bunch of, what percent of individuals responded to kind of a specific treatment? Was it just yes or no? Did they respond? Did they not? And then, oftentimes if we're testing an actual treatment, it's not just the average or proportion of kind of that one group, but we're often comparing the average or proportions between two groups. Again, kind of going back to the height example, maybe I'm not interested in the height of, the average person in the US, but maybe I'm comparing, are people in Washington state on average, are they taller than people in Idaho? So then I'd grab 50 people from Idaho, 50 people from Washington, and I compare their average heights as that sort of point estimate. Again, that single best guess for how I think the heights differ between the states on average. And kind of going back to my app example, that could be, among those who are given the app, we found that again, there was a 15 minutes kind of higher physical activity compared to those who did not have the app. Again, this is just kind of, a made up scenario, but that would be something like a point estimate that we may see. Oh, we see those with the app had 15 minutes more physical activity per week in our sample. But it's really important to note that, even though this point estimate is our best guess, again, we're not generally really confident that this is the exact value. Again, going to the height, if I grab 50 people off the street and take their average, and then I grab a different 50 people off the street and take their average, it's unlikely that those two heights will be exactly equal for those averages. I hope they'll be somewhat close, but I know there's just going to be some difference based on who I happen to sample. And that's the same way with kind of any treatment. Some people are going to respond better and some people are going to respond kind of worse. So it's just part of it's kind of the luck of the draw of who you happen to kind of sample. And you're going to see slight differences if you were able to repeat that study. So, if in theory we were able to repeat the study, rather than a 15-minute difference, we may have found a different sample had a 10-minute difference. And then if we were able to grab another sample, we may have found they had a 17-minute difference. Now, the problem is we're not able to actually repeat the study, right? So we kind of do one study, we get this point estimate, but we still need some way to capture this kind of idea that our estimate isn't perfect and that it would vary if we had different samples. But again, we often don't have the resources to kind of just repeat the same study over and over and over again. And this is just a picture that's kind of meant to illustrate this idea of how point estimates could differ from multiple samples. So I'm assuming that they're all taken from the sort of same population, but depending on the specific sample I grabbed, I may see, and we have kind of the different study numbers on the y-axis, but the different sample that I grabbed will change the actual estimated value kind of a little bit. And again, this is what we want to capture without having to actually repeat this study, 5, 10, 15, 20 times. And that brings us to this idea of variability. So variability, again, is this measure of how much we think those estimates really differ. So again, one way that we could actually capture this is if we, again, conducted, 20 different kind of trials of the exact same study and measured how much those estimates differ. Again, we kind of talked about not being able to kind of really do that. What we instead have is this kind of idea of standard error, which is something we can derive both from our data as well as with some kind of theoretical kind of understanding. So I'm not going to get too deep into kind of the actual calculation of standard error, but just wanted to discuss the components that go into the standard error when we try to kind of calculate this. So really the two components that really go into standard error are how much variability is there amongst the individuals in our sample. So previously we were talking about variability between samples. To calculate the standard error, to kind of try to measure that, we first need to calculate what's the variability within our sample. And then the second component is our sample size, right? The larger the sample size, I'm kind of more confident in my estimate. Again, back to that height example, if I sample 5 people on the street, I'm not real confident that estimate is going to be really close to the kind of the state average. If I would sample, 3 million people, then all of a sudden I'm like, that's a big chunk of the population. I probably have a pretty good, estimate of what that is. And I don't expect there to be a lot of variability between a different 3 million people that I sample. So again, those are kind of the two components of standard error, the variability of individuals and the sample size. And the more variability we have of those individuals and kind of the more spread out our population is, the higher the standard error is. Because, if our individuals are really spread out, then it's possible that I get a random sample from one end of the spectrum, the really low end, but then if I draw another sample, I get a kind of a group on the very high end. And because they're really spread out, those values are going to look very different. If all the values are really close together amongst individuals, then that means, even if my sample is slightly different, they can only really wiggle a little bit because all those values are very close together. And then I kind of mentioned this, and this can be worked out, mathematically. This whole larger our sample size, the smaller the standard error. But again, I think this conceptually, kind of the more data we have, the more confident and the more precise we are in our estimates, I think is kind of an accessible intuition to kind of understand rather than having to dive into kind of the specific equations. The next component, which is again kind of building off of both our point estimates, which again is our single kind of best guess, and the variability, which is an attempt to estimate how much we think that kind of single point estimate could vary. Confidence intervals is really combining those two together, and it's really giving us a range of values where we think the true value lies. So rather than a single point estimate, which again, we don't think is probably 100% accurate, but we think it's, probably in the ballpark. And unlike the variability, which I think is, it's intuitive to understand what variability is, but it's not necessarily intuitive how that translates to our kind of point estimate. This confidence interval takes that variability with our point estimate and gives us this range that's really, I think at least, easy to interpret. So it's basically a confidence interval where we say kind of how confident we want to be. And this is often, 95% confidence, but you may see this in kind of other studies where it's 90% or even 99% confidence. But it's basically saying whatever level of confidence we choose, this confidence interval that we created will contain the true value that percent of the time. So again, if we choose this 95% confidence interval, we create this interval based on our point estimate and our variability such that 95% of intervals created this way will contain the true value, while 5% will not contain that true value. Now, we never actually truly know if we're in the 95% or 5%. So we don't actually know if we're capturing the true value or not. But again, 95% of the time, it will contain the true value. So again, we're 95% confident, not 100%, but we're 95% confident that that interval will contain that true value. So for the example, for the app with the minutes, if we have a confidence interval that's really 10 to 20, and again, our point estimate was 15, we're really 95% confident that the true impact of the app is somewhere between 10 and 20 minutes. And this becomes a lot more kind of useful because now we actually have a range where we are very confident the true effect is. Again, unlike that 15, which we weren't very confident that it was exactly 15, we're now very confident that that actual effect is somewhere between 10 and 20 minutes. Another way I like to think about kind of confidence intervals and what they're doing is, again, kind of going back to that height example. But, if I was kind of, came into a room and kind of told everyone, hey, I just saw somebody who was, 6 feet tall, kind of out on the street, how many people would be kind of really impressed? Like, whoa, you saw somebody who was 6 feet tall. And kind of my assumption is not very many people would be kind of that impressed. And what's really going on here is it's not that people are not impressed that I saw somebody who was exactly 6 feet, because seeing somebody exactly 6 feet, kind of, to the fraction of an inch is actually really, really rare. There's very, few people who are exactly 6 feet tall. So that's a very rare occurrence. But what people I think are often doing are kind of framing this as, 6 feet, it's not necessarily 6 feet that I'm interested in. It's really, anywhere from 5.5 to, 6'3" is a very common height in that range. So even though I'm talking about 6 feet, I think people intuitively create this sort of range for where they think the majority of people lie. And that's sort of what I like to relate this confidence interval to. It's very unlikely to see 15 minutes exactly, just like it's unlikely to see 6 feet exactly, but it's very common to see that true value in the range of 10 to 20, just like it's very common to see somebody in the height range of 5.5 to maybe 6'3". And this is just an illustration of kind of those confidence intervals I've created over those exact same point estimates that we've had before. So I kind of denoted this dark black line here, which is what I know is a true value because I'm just making up this data and simulating it. Now, we generally don't know what that vertical black line is. So I'm using it to represent the truth to kind of illustrate it here. But in practice, we don't actually know what that black line is. And then I have the 5 different kind of repetitions of the study that I do. I have that point estimate, and then I have those bars representing the confidence interval. And we can see in this case, all 5 of those bars contain the true value, even though not one of those points represents the true value, right? It's just going back to that idea that these point estimates generally are not exactly the true effect. But again, in many of these cases, they're very close to that true value. And once we create that confidence interval, we now see the true value tends to go through those. Now, I've only shown 5 studies here, but because this is a 95% confidence interval, if I had shown 20 different studies, I would expect only 19 of them to contain this kind of black vertical line, and one of them, the interval would be completely either to the right or to the left of that bar, just kind of by chance. And again, we don't know which one we have, but the fact that 19 out of 20 do contain the true value means we're fairly confident that whichever one of these intervals we do have, it's more than likely than not to actually contain that true value. The last value I want to talk about, and I think this one is, perhaps the hardest to understand because I think it's very easy to misinterpret kind of what a p-value is. But the last component that we really want to address with statistics is we want to know if our results are due kind of just to chance alone. Right, I've just talked about, we're going to see this variability between different samples. So is it possible that our sample just looks good just by chance, or does our sample look good because there's actually a treatment effect kind of going on? And now kind of straying away from the heights, but if we think about this as, flipping coins, if I flip a coin, 4 times, I could get, 4 heads, I could get 3 heads, I could get 2 heads, I could get 1 heads, or I get no heads. And all those can happen even if I have a fair kind of 50% kind of coin. It's less likely to get 4 heads than it is to get 2 heads if my coin is fair, but it's still kind of possible. So if I get 4 heads in a row, I want to know, what's the chance of getting 4 heads just by flipping a fair coin versus, do I think this coin is maybe weighted and I'm more likely to get heads or not? And maybe 4 flips is hard to come by, but if you flip a coin 100 times and 100 of those coins come up heads, that's still possible to occur due to chance, but it's so unlikely to flip 100 heads in a row with the fair coin that you then want to conclude that there's, that coin is weighted. I no longer trust that coin. I no longer trust how you're flipping it. I don't trust you telling me the truth. Whatever that conclusion is, you're concluding that these flips are no longer fair. So that's the idea behind this p-value is, how unlikely are our results to chance? What's the probability of seeing our results if it was just a coin flip? And again, I kind of talked about this before, but I just really want to kind of drive this home that a treatment can look effective in our sample, even if it's not just by chance. Again, our sample is just a portion of the population. And what we really want to do is understand, does a treatment work in the population? We don't really care if it works in our sample just for the sake of working in our sample. We're really using that as a means to try to capture what's going on in the true population. So it's just kind of along the path of capturing what we want, but we're not going to stop at that sample and say, oh, help more people than not, we're good. We need to try to figure out, well, how often would we see more people helped just by chance alone? So to do this, I want to first kind of walk through kind of a thought example, and then we'll talk about how this is kind of done in kind of actual, kind of practice. So the first thing we need to do to understand this p-value is we first need to imagine that we create a scenario where there is no treatment effect. So, I talk about this app that we're hoping works, but what I want to do is create an app that I know does not work. And again, this is just a thought experiment. This isn't how research is actually done. But we first create the scenario where I develop an app that I know is no longer effective. I know it doesn't work. And then what I could do is I can give that app to different samples of people and compare it to those who did not have an app. And I know on average, there will be no treatment effect because I've created an app that by design does not have a treatment effect. But I know that individual samples, there may be some treatment effect. It could be positive in some cases. It could be negative in some cases. Again, but just due to chance, I know there's going to be some differences in the treatment effects, even though in the population, I know there is not a treatment effect. And then I can record kind of all those different estimates from all those different samples, and I know exactly what my estimates would look like if there was no treatment effect. And this is what we call kind of the null distribution. It's sort of, what distribution of effects would I expect to see in a sample if I knew there was no effect in the actual population as a whole? What we then do is we then run a study with the app that we want to test, which we think is going to help people. And we basically see amongst all the different sort of fake scenarios with no treatment effect, I compare where my value is from my true study and see how rare it is. Am I kind of right in the middle? And so, this is really common to see even if the treatment doesn't work, or am I really at the extremes of, only, 0.01% of the time would I ever see results like this just by chance. Again, we don't know with 100% certainty whether it's by chance or by treatment, but if it's only likely to happen 0.01% of the time, then I'm no longer confident it's happening just due to chance. I'm more likely to believe that that treatment is actually kind of very effective. So that's the kind of the big picture idea of p-values, and how we kind of work through it kind of in a thought experiment way. How we do this in practice is we often first calculate our point estimate, and then we theoretically, so we can kind of make these theoretical assumptions that allow us to kind of invoke some mathematical properties to calculate what we think the theoretical distribution is like. Or we can basically mimic that thought experiment I just walked through, but rather than running it in actual people, we can just run it through simulations to get an idea of what we think would happen if there is no treatment effect. And then we just see how frequently are those sort of theoretical or simulation values, how frequently are they as extreme or more extreme than our specific kind of point estimate from our sample. So we're basically counting up, what percent of the time would we see results like ours just by chance if we knew there was no treatment effect? And that's exactly what this p-value is. To then conclude whether something kind of statistically significant. So if you're reading literature, you'll often see this idea of statistically significant, but basically we just use statistically significant to indicate that that p-value is smaller than some cutoff that we've determined kind of ahead of time. So the chance of it occurring, even if there was no effect, is lower than a threshold that we've set at the start of the study. Often this is 5%, so often kind of a p-value less than 5% is considered statistically significant, but you will see that potentially vary based on the study, based on kind of where it's at in the research, based on what the researchers are trying to conclude. But 5% is kind of that industry standard that we generally start with. So this is just meant to, kind of illustrate, I find pictures are helpful for me. So this is really just meant to illustrate this idea of p-values in a more kind of concrete kind of way. So what I have right here, so this histogram tells me if I flip 10 coins, I have the number of heads flipped on the x-axis on the bottom here, and on the y-axis going up, I have the probability of that kind of occurring. So again, you could flip 10 coins over and over and over and repeat that a million times, and you could create a graph like this. But again, we have some kind of mathematical properties and equations that we can actually just calculate these probabilities directly theoretically. So that's what I've done here. So I know that the probability of getting 0 heads out of 10 is almost 0. But if I look at what's the probability of getting exactly 2 heads, I'm nearly about 5%. Getting 5 heads, there's almost a 25% chance for that to happen if I flip 10 coins. So this is the distribution I'd expect if the coin is fair. I then, grab some coin that may or may not be fair, I don't know, and I flip it 10 times, and I come up with 7 heads. So what do? We have this nice distribution of what a fair coin should look like, and then I can look at, where was 7 heads, just kind of this first gold bar here. So there's about a, 12.5% chance of getting exactly 7 heads. But for the p-value, I also want to know what's the probability of more extreme. So it's not just exactly 7 heads. I also want to know, what's the probability of exactly or kind of greater than. And again, this goes back to that height example. The probability of finding somebody exactly 6 feet tall is pretty rare. But the probability of finding somebody 6 feet or taller is not nearly as rare. And again, that's kind of that intuition of most people wouldn't be impressed if you saw somebody who is 6 feet tall, because they're thinking, oh, there are a lot of people who are 6 feet or taller. They're not thinking, what proportion of people are exactly 6 feet tall. So in this case, for that 7 heads, I add up the 7, 8, 9, kind of 10 heads probability, and I find that that's about 17%. So my p-value in this case would be 17%, which means that if I flipped a fair coin, I would expect 7 or more heads about 17% of the time. And again, using that kind of cutoff of 5%, we're not below that threshold. So we're basically saying 7 heads is not rare enough that I'm willing to kind of bet against a fair coin. 17% chance, that's fairly common to occur. I think there's a good enough chance that this coin is fair. I'm not betting against it. If we instead, again, looked at, maybe 9 heads out of 10. I think intuitively, everyone would think, oh, this is more extreme, getting 9 than just 7 heads. And if we look at kind of what the probabilities would be, down here we have maybe it's about 1% for 9 out of 10 heads. And we'll just say it's 0%. It's not exactly 0%, but it's pretty small for 10 out of 10 heads. But now our p-value is about 1%. There's only a 1% chance that we would flip 9 heads with a fair coin out of 10 flips. So at that point, I may start tending to believe that I no longer think that coin is fair. 1%, that's so unlikely to happen. I think instead that that coin is weighted such that the probability of heads is greater than 50%. And again, that's kind of what the p-value is. That's how it's kind of used. But I think this picture helps illustrate that, maybe better than all the text on the previous slide did. So I just want to kind of, briefly, summarize, again, why we use statistics and kind of the 4 values that I think are the most kind of important to kind of be aware of. Again, statistics is really kind of our connection between using a sample to make some conclusion about a population. So, if we were able to test a treatment on everyone, we wouldn't need this whole field of statistics. But what we're really trying to do is use a sample to make a claim about a treatment for a population that it represents. And making that kind of bridge so that we can, again, kind of, look at new therapies, new treatments in an effective way. Because if we had to test it in everybody across the US, it would be very resource intensive, and we wouldn't really be able to make much progress in actually kind of, developing new treatments, because it would just take too much time and money to test it across the entire population. So to get at that, again, we really kind of use these 4 different values. The point estimate is really the single best guess that we can get from our data. But again, we know that the single best guess is probably not perfectly kind of accurate, and we know that it can vary based on our sample, which then led us to this idea of variability, which is really how much our point estimate will differ if we could resample. So if we could conduct a study again with a different subgroup of individuals, how much do we think that point estimate would differ? Again, we can't actually keep doing studies over and over and over again, but we get at this sort of theoretically by looking at how much do the individuals in our study vary, as well as the sample size, and those two combined tell us sort of how much we expect our point estimate to differ if, in theory, we were able to repeat this study over and over and over again. Kind of combining point estimates and variability give us this idea of confidence intervals, which really gives us this range now where we think the true value is. So again, even though a point estimate, we're not really confident that that point estimate is exactly correct, we are confident that the true value is somewhere in this range that we're able to create. So again, I kind of know where I'd expect the lowest value to be, and I know where I'd expect the highest value to be. I don't know where we are in that interval, but I know that there's a very, with high confidence that confidence interval contains that true value. And then the last is this p-value, which is really a measure of how likely our results are to occur just by chance alone if we know there is no effect present, right? So we, again, kind of create this artificial scenario where we know there is no effect. We then looked at, okay, well, what does it look like? What does this distribution of outcomes look like if we know there's no effect? And then we compared our specific effect to that distribution of kind of values when there was no effect. And I'm just going to again, I think this is a really important kind of point to drive home. So I'm just going to jump back to this very quickly. Again, all these bars indicate the probability we'd expect if the coin was fair. So again, we're assuming there's no effect, but we can see that the outcomes could still differ based on a specific sample. And we then compare our observed value, this 7 heads here, and we figure out, how unlikely is that, or kind of a higher number of heads to occur just by chance alone. And that gives us that p-value that we can use to determine if we think this treatment is actually going to be effective in the population or not. And that's what I have today. I'm happy to take questions. I'm happy to dive into any of this in greater detail. So yeah, so any questions, happy to answer them.
I'm just going to stop the recording.